and when school resumed I was told about the Young Enterprise Scheme, which is New Zealand's largest business competition with over 1,000 teams entered in 2022. And obviously I entered, which meant I had just under 12 months to make something out of my plastics project. Currently, things were not looking good, as one sheet worth of product took 5.5 hours to produce, then an additional 8 hours to cool, which limited my production capacity to 7 sheets per week. And to build a successful business, I needed to significantly reduce these times, which meant rethinking my production process, and what better place to start than with sourcing plastic. On average, I was collecting about 30 used bottles a day from local cafes in my area. However, each sheet needed approximately 60 to 80, which was significantly limiting my production. So I reached out to Anchor Milk, the company responsible for producing, delivering and collecting these milk bottles from cafes and restaurants nationwide. My email eventually made its way to the director of Anchor Milk Canterbury, and we arranged to meet for a coffee. During our conversation, I presented my idea and requested their assistance in sourcing plastic for my project. And the director, Andrew, was very supportive of my initiative and offered for Anchor to start delivering used milk bottles to my production site whenever I was ready. So that got me happy, which meant I now had a near endless source of used plastic. Additionally, as part of the Young Enterprise Scheme competition, I was given the opportunity to apply for seed funding. To enter, I put together a 60-second video explaining my business and what I'll need the money for. I ended up winning $250, which was definitely helpful as this project was about to get really expensive. Sheet production was now the primary constraint affecting my scalability. To overcome this challenge, I realised I would need to rethink and revamp my entire setup, taking into consideration everything I had learned. And so I began with building a new mould that had a full aluminium interior, was heated, cooled, height adjustable, user friendly and could withstand constant use. And after many iterations, this is the design I came up with. For heating and cooling, I decided the best option was using a closed loop water circulation system, similar to the ones used in actual injection moulding machines. These work by pumping cold and hot water through the mould. In my case, I designed the water loops using aluminium box tubing, which gets held down by 9 welded tabs with an inlet and outlet at each end. This then gets sandwiched between a 6mm aluminium plate and an 18mm plywood board, which is all held together by bolts. To stop it from getting crushed under the 4 tons of pressure, I added these 20mm spacers which more evenly distribute the force. This 3-layer design then gets repeated on the bottom so they're both mirrored. This way, both sides of the plastic sheet can be heated and cooled. To create the 4 sides of the mould, I used 6mm aluminium plate screwed to 18mm plywood, which is then supported by a wooden edge. A piece of 18mm plywood is then screwed to the top layer. This provides strength whilst limiting how far the top can be pressed. To adjust the thickness of the plastic sheet, I designed a removable front. This allows the user to add wooden spacers under the bottom plate which lifts it up or down, in turn controlling the space in the mould. The most challenging part of building this mould was ensuring the aluminium water loop functioned properly. It needed to lie flat against the aluminium plates for efficient energy transfer, which meant all the welds had to be ground flat. However, this kept introducing pinhole leaks, and even after getting it welded 5 times, I could not get it watertight. So I finally gave in and consulted an engineer named Graham, who I'd met at a robotics club. And he suggested using thicker aluminium and connecting the water loops with tubes instead of the 45-degree angles, which reduced welding, complexity and chances of warping. And after rebuilding the water loop with these iterations, I had no more problems. And as I mentioned earlier, if you'd like a more detailed look at how I built everything, you can check out my other video linked below. Soon, June rolled round and I had my first Young Enterprise pitch competition against the teams in my local area. At the time, I was only selling letter stands, so my goal was to sell the judges on the versatility and future potential of my recycled plastic sheets. My speech emphasised that the letter stands were merely a proof of concept to demonstrate the market's acceptance and demand for recycled plastic products, and the customer's readiness to invest in sustainability even at a slight premium. Furthermore, I highlighted the adaptability of my production process, which allows for a wide range of products to be made using sheets and a CNC machine. And I think the judges were impressed as I scored 94%, which allowed me to progress to the regionals competition. So with that over, it's back to production. At this point, the workshop was becoming increasingly crowded and challenging to work in. I was making and selling letter stands whilst trying to build gradually larger equipment. The constant cutting was contaminating the plastic, and the limited space was becoming a massive constraint. So being the solutionist I am, I spent the next week convincing my parents why my production line should get the car's parking spot in the garage. And whilst they weren't particularly happy, I eventually got the green light. So using leftover wood from an old shop fit out, I constructed benches to hold the production equipment. Additionally, I upgraded the deteriorating wash station using a metal shelf and 2 second-hand sinks. I then used all the fittings from the old wash station to make the new one. I also repurposed another shelf into a drying rack. I then moved over all my old production equipment so I could continue making sheets. With the additional space, I was now able to continue my venture into further debt. To build the mold's cooling system, I opted for a straightforward solution, utilising a used 200 litre oil drum as a reservoir and relying on ambient air for cooling. To handle the heating, I repurposed an old fire extinguisher and integrated a heating element to create a hot water tank. The whole system operates by toggling between the 2 reservoirs using 4 valves. I did this to simplify plumbing and reduce costs by relying only on a single pump. And to increase my odds of everything working first time, I conducted numerous tests to verify the pump, water loop and plumbing could withstand the stresses of pressurized hot water and constant repetitive use. And once I was confident, I integrated the full system with the mold. And to precisely regulate the temperature of the hot water, I wired up a PID controller, and like before, I made sure to verify it all worked before permanently hooking it up. Once everything was plumbed up and ready to go, I filled the tanks with 250 litres of water. This step was helpful as all leaks were now easy to identify. However, it also led to the garage flooding, which is when I realised I might need a drain valve. Problems aside though, I achieved impressive results, heating the mold to 55 degrees and cooling it to 18 degrees in under 5 minutes. While simultaneously developing the mold, I was also working on a new shredder. Up until this point, I had been using the mulcher to shred the plastic. However, it was far from ideal. The mulcher was incredibly loud, messy and inefficient. I knew that what I really needed was an industrial shredder. Therefore, I contacted various shredder companies in New Zealand and explored used equipment options. I also reached out to shredder manufacturers in China, but their prices were beyond my budget. This led me to building my own. I used open source shredder plans from Precious Plastics as a starting point in Fusion 360. I then modified and refined the design to match my needs. My biggest challenge was getting all the tolerances to fit correctly, and since the minimum order size for laser cutting in my area was $200, I had to get it pretty much perfect first time. Sourcing materials also posed a big challenge. Not a single steel shop in New Zealand stocked the hexagon bar I needed for the shredder shaft. Fortunately though, I came across a bolt manufacturer who had an off-cut piece available. Then finding an appropriate drive system that I could afford proved to be another big hurdle. Thankfully though, after a lot of searching, I came across a second-hand 1:30 ratio gearbox and a 2.2 kilowatt motor for a really good deal. Overall, the shredder assembly went together surprisingly well. I did struggle to get the tolerances right so the blades would spin smoothly. I also made the mistake of cleaning all 120 steel parts in water and not drying them properly, which meant they rusted, so I had to resand and re-clean them. This probably caused the tolerance issues. I then forgot to dispose of the cleaning rag I used, which caught fire when I was welding. So it was an enjoyable experience. The garage was now looking more like a production line, and for a short period of time I was really excited. However, all that fell apart when I actually started using the equipment and realization hit on just how far this was from ready. The equipment was still not functioning properly, and to be honest, up until this point, laziness was generally prioritized over safety and aesthetic appeal, which was kindly pointed out to me by literally everyone. So I stopped taking orders and spent the next month rebuilding and rethinking the overall design. Given the poor condition of the heated press machine, I focused on repairing this first. So I disassembled the entire unit and began by resurfacing the plates to remove burnt plastic. To prevent the heating blocks from coming loose, I replaced the bolts with larger ones. To make loading plastic into the machine easier, I cut the front off and replaced it with an articulating arm. The machine was then re-welded, sanded and painted. I replaced the worn out scissor jack with a new one and added an additional bearing to prevent future wear from all the pulling tension. Proper thermal paste was applied to the heating blocks and cartridges. Additionally, I added brackets to the top plate which secured the Teflon sheet in place. Finally, after reassembling the machine, I ensured electrical safety by installing covers and heat shrink tubing over all exposed wires and connectors. Next, I turned my focus to the shredder. To minimise the mess it generates, I constructed a hopper from MDF and mounted it on a hinge, which provides easy access to the blades for maintenance. I then added an acrylic hatch which allows the milk bottles to be safely loaded into the machine. Additionally, I added a funnel to the bottom which helps further guide the plastic. Then to make it a little safer, I rewired the motor and added an electrical cover. Lastly, I swapped out the bolts on the shredder coupling as they were bent and added new plastic sleeves. My next task was replacing the perimeter screws of the mould with heavy duty bolts. This was to prevent the plastic from bending the sides. I then turned my attention to a long time issue, which was sourcing enough power to run all the equipment. The recent addition of the shredder only heightened the problem, leading to the circuit breaker frequently tripping. So in collaboration with my electrician, we came up with a solution. We wired the shredder to an external 18 amp caravan plug. The water heater and heating machine were then powered by two separate 15 amp plugs, while a standard 10 amp double plug powered the fans, fume extractor and all other equipment. The total power consumption of this setup reached an impressive, yet somewhat unsettling 10 kilowatts. Then after I finished wiring the remaining equipment, I got the electrician to inspect all of my grounding connections. Next, I had to find a solution to my plastic shavings clogging the school's extraction system, as people were starting to notice and they weren't happy. Despite using a cyclone extractor to gather the shavings from my cutting process for reuse, a significant amount of plastic was still getting past. So I bought a 200 litre plastic drum which I screwed to a board that I cut to fit snug over a standard rubbish bin. Then I designed and 3D printed an inlet and outlet to create my own custom cyclone extractor. And if you're curious, this basically works by creating a spiral vortex that separates the plastic from the airstream. And this machine worked really well. Lastly, I worked to improve the speed and cut quality of the CNC machine. I conducted research and numerous experiments with different cutting bits, tabs and toolpaths. I found that a 4mm single flute cutting bit yielded the best results, and overall I was able to reduce the CNC time from 1 hour to only 25 minutes. And I was able to save an additional 45 minutes as the letters needed less sanding and cleanup. Despite having rebuilt most of the equipment, I continued to face significant production challenges, which were becoming increasingly frustrating. Out of every 10 sheets made, approximately 2 were good, 5 were usable and 3 had to be scrapped and remelted. However, I soon realised that most of my issues were no longer related to the equipment, but were rooted in my overall processes. Therefore, to improve the consistency and overall quality of the plastic sheets, I spent the next 3 weeks experimenting with different variables. And to spare you on the details, this is the complete process I came up with.
Milk bottles are delivered to my house weekly by Anchor.
Then I remove the labels from each milk bottle and clean the exterior by hand. The wash station then cleans the inside using pressurized water. Afterwards, they are placed onto the drying rack. Once fully dry, I inspect the inside of each bottle using a flashlight to check for any dried milk residue. If a bottle is dirty, I have to cut off the bottom and clean it by hand. Otherwise, it goes straight into the shredder. I then lay down 4 pieces of Teflon sheet in an overlapping pattern and mount 1.5 kilograms of plastic at 200 degrees. Following that, I add an additional 900 grams of plastic. Once it's fully melted, I remove the plastic and roll it by hand to mix the colours and remove any air bubbles. Next, I lay down wooden spacers in the heating machine. The mixed plastic is then placed back in and heated at a final temperature of 220 degrees. The reason for reducing the plastic's dimensions is that I found it compresses more evenly in the mould. I then activate the pump to circulate the hot water. This raises the mould temperature to 70 degrees. Following that, I apply a light coating of vegetable oil to the interior of the mould. The next step is transferring the plastic from the heating machine to the mould. This is the most challenging part and must be done in under 60 seconds, otherwise the plastic solidifies, and this process involves removing the plastic from the heating machine, peeling off the Teflon sheets, transferring the plastic into the mould, securing the top of the mould, then a large plate gets added before raising the jack. Then I switch the circulation system over to the cold water, which cools the entire sheet in 30 minutes. Next, I take the sheet to school where I cut off the excess plastic using a bandsaw. Then I run them through the thicknesser, which trims it down to 10mm thick. I then screw the sheets down to the CNC bed at the far corners. This holds it in place while the CNC marks the pilot holes. This is to make sure the screw placements are in the right place to prevent lifting and collision with the cutting bit. The CNC then follows two tool paths. The first cuts the inside of the characters and the second cuts the outside. This is all done in one pass using a 4mm single flute cutting bit. To prevent the letters from detaching during the CNC process, I use tabs, which are then later removed with a knife. Finally, I cut the letter stands from discarded pallet wood and do a final inspection before shipping the product. All of the offcuts and shavings can then be collected and remelted into a brand new sheet, which cuts down the production time as this plastic doesn't need to be collected, cleaned or shredded. With my more optimized equipment and processes, I cut my production time down from 810 minutes to under 80, which gave me the production capacity to start scaling my business.